Bismillahirrahmanirrahim. Hello everyone. So today we are going to be taking lecture number 30 about state space modeling. And in this lecture we try to cover state space modeling in two aspects. And I know that state space modeling is very different from what you have taken before. However, it is much related to process modeling. So what is the idea of state space and why are we taking state space? If we just can recall that, very beautiful. I'm starting with very beautiful colors. Okay, so let's start. Okay, let's start with the idea that we had developed a group of model equations, right? And we start with the mass balance and the energy balance, if you can recall. And it was important for us to start with those law of conservation, so that we can be able to study how does height change with time, and how does the concentration changes with time, and how does the temperature change with time, and so on, right? And when we studied all that for different systems, and then we said that, well, it's beautiful to study the relationship between how does the height change if the input flow rate changes, right? How does the height change if the output flow rate changes? How does the concentration change if the input concentration changes? And how does the output concentration changes if the input flow rate is changing? How does the concentration change if the temperature input is changing? How does the temperature change if the cooling coil or the temperature of the cooling coil is changing, and so on? So we had many different studies, right? We had many different studies, and it was good to have these transfer functions in our life, because these transfer functions they just made us understand our process. It was really beautiful. It was a good journey to go through the transfer function. So we understood the process, and actually we were able to study the process, and then we were able to be controlling the process in the next course when you're going to take it. Okay. And we call this the time domain. Remember that? We said that that this is the time domain and this is the S domain. Now, what you are trying to take here in the state space modeling is that instead of representing this in the time domain, can I represent it in a matrix or a state space model domain? It's like a matrix domain. It's a space domain, right? And this is where their name is coming from. It's like a matrix. Okay, so in our state space model we have a matrix, and other than we have a matrix, we have states, which means the differential equations. Okay, the differential equations that we have. So we want to represent our system in which we have all our differential equations in a matrix format. Okay, so all differential equations, the states that we have are represented in a matrix format. And how do we do that? We do that through two equations that we have. We have two equations, and this is the way how we usually start explaining state space model for chemical industries, which is different when you study, for example, electrical engineering. There could be a different approach to that, and I'm going to come to that approach because it is important as well to know how to go from the state space to the transfer function, from transfer function to back to state space. All that is really important, and we can go through it and know it. But just to build up the idea, this is the way or the approach that I prefer. So what are the two equations that we have in state space modeling? That is my first equation, and that is my second equation. So these are the equations that we have for state space modeling. So in this state space modeling, what do we have here? what we have here exactly is that these states or the differential equations, and as we have, for example, a state like dx by dt or dy by dt or d temperature by dt or d height by dt. So we have d height by dt and we have the height term within the equation. So these are the variables related to the state variables. And here u are the inputs. Here u are the inputs. So in the inputs I have the input flow rate, input concentration, input temperature, and so on. And when I build my system here, y is the solution. Y is the solution. That means this will tell me how, this is the solution. Remember the solution, we said y is equal to km to 1 minus e to the power minus t over tau. So this is the solution. Tells me that if you solve dh by dt, the solution is going to be h, and here h is going to tell you how does it change with time. And here C is the identity matrix, to identify as well, to identify what you want to represent as a solution, to identify or select from the solution. So you want to select from the solution. You don't want the whole solution, you want part of it. Okay, for example, I'm solving here within the matrix, I'm solving height, temperature, and concentration. I just only want to see the concentration only, so I can identify through the C term. Okay, what about D? D is just zeros. Okay, so it's part of putting it to the system just to make my system become solved. Okay, so that it can be solved. So this is the basic of it. So I have my x dot are the state variable, they are the states, and I have my x is the variables of that state. So h dot h, t dot t, ca dot, which is dca by dt, ca. Here are the inputs, so fi, cai, ti, tc, and so on. Here's the solution, so it's dh by dt, the solution is h. And here's the identity matrix to select from the solution, and D are the zeros. What else do we need to know before we start our problem? We also need to know that about the dimensions. So the dimensions, okay, the dimension of let me say it the other way around. The dimension of C is like the dimension of A. This is if you want all the solution. Okay, this is in the case that all solutions are required. So this is in the case that all solutions are required. And the dimensions of D, okay, I know that I'm building something new here for you in your head, so I'm sure that you're saying, okay, what's going on? I still didn't understand. I'm just building the basics, right? I'm building the base that I can now explain based on that base, okay? Dimensions of D is like the dimension of B. Beautiful. I think so. This is the main thing. That's all what you need to know. Now, I think so. After I have spoken about the dimensions, now I need to talk about an example. Please give me an example. And we are going to take the simplest example that we had taken before, in which we had a CSTR, or let me say a simple thing that has no reaction at all, and then we're going to take it one step ahead from there. So this is my input flow rate, this is my output volumetric flow rate, and this is the mixing process that I have here. So what do I want? What do I want exactly? If you remember that we wanted to know how does the height change with time, and knowing how does height change with time, we already did this before. We are going to write our equation, which was dm by dt is equal to m in minus m out. And of course, remember, if you want height, we can get that from the overall mass balance. So here we are going to have rho a dh by dt is equal to rho n fn minus rho f. I'm going through this again. I know you already went through this many times. And then you're going to have like dH by dt is equal to Fn over area minus f over area, and f here actually is alpha square root of h divided by area. So that was the equation. If you can recall, that was our equation, and based on which we started linearization and deviation, right? We are going to do exactly the same. We are going to do exactly the same. And in this case, like this is what I'm going to do here. I'm going to do exactly the same thing, like dH prime by dt, which was a function of the state variable and the inputs, okay, and the inputs. And you can see that I'm having exactly the same thing. I didn't do anything different from what we had taken before. And this is like equal to df by dh into h prime plus df by dfi into fi prime. Come on, Doctor. I think so you're telling us something exactly of what we have taken. Where's the state space modeling? Hold on, don't worry. We are going to get to that point. Now, if you can realize something beautiful that we can see here. What is that? I can see x dot here, which is dH by dt, the differential equation. And I also can see my first matrix, which is df by dh. You can see df by dh, okay? And I also can see my h prime, which is part of my dh by dt. So this is like x dot, and this is the x, okay? So this is like the x that I have here. Plus the b term here, which is this df by dfi, and then I have u are the inputs, and in this case my input is fi. What? Okay, there's nothing. I didn't do anything yet. Everything is exactly to what we have taken before. So what is going on, right? And I think everything that we had taken before is exact. So what is the difference here? Actually, here what we are dealing is 1 by 1, and this is why it looks exactly to what we have taken. As we go 2 by 2, you're going to see that things are going to be similar, but it's going to be in a bigger matrix. So here I'm representing like A is in a matrix, even though that is a 1 by 1, right? It's 1 by 1 term. Okay, and this is what I have. That is my A. And that is my B. So I have the value of A, I have the value of B. What about C and D? And so going to C and D, if I write my solution, so y is equal to Cx plus du. And in this case, my C is equal to the dimension of A. A is 1 by 1, so my identity matrix is just 1. If you just can recall, the identity matrix is putting all the 1 in the diagonal, and it is something like that, right? But in this case, if it's 1 by 1, that means I'm going to select only that part. If it's 2 by 2, I'm going to select that. If it's 3 by 3, I'm going to select that. Okay, so it's 1 by 1. And plus du. What is the dimension of B? It is 1 by 1 as well. So I'm going to represent this as 0. And in this case, talking about D, D is zeros, right? If it is 3 by 3, it's like that. It's all zeros. If it's 2 by 2, it's the only zeros. If it's 1 by 1, it's only that zeros, right? So that is, so that is the C matrix. And what about this D matrix? It is 0. And this is the solution. And by the way, this is the solution. All one you need to do is you enter the values of A, B, C, and D in MATLAB, and you just write a very small code. It's not a small code, it's one line script. It's not even a script, it's just one line small code. And you have the answer, okay? You have the answer, SS, A, B, C, D. So that's how it's written in MATLAB, like state space, A, B, C, D, and you're going to get it, and then you say step. I want to have a step input for all those. So it is straightforward. It's very simple. as you can see here, this is the way how we can get our state space matrices. Okay, so you're asking me, so how is that going to come the exam? I'm going to ask you to find the matrices of the state space model, right? Of the state space model, and the matrices in this case are what? They are A, B, C, and D. So you're going to find that. And then, of course, if we had some time, or if we had the capability of doing this, to do it on MATLAB, we will do it. But as through our position here, we are going to be only requesting you to find the matrices. Okay, what else? Can we take another example? Yes, we are going to take another example. And in this example, we are going to have something that is a little bigger than the one that we had here. And in this case, I'm going to consider, for example, I have two tanks in series. I'm just trying to take the simple examples because we need to build the idea here. Okay, so we don't need any other ideas that will complex things in your head. So keep it simple so that things get normal into your brain. Okay, so this is what we have here. So we have a simple system. We already solved for these two heights, right? We already solved for height 1 and the similar would be for height 2. Considering them, the tank 1 and tank 2 are the same. So tank 1 is equal to tank 2 in terms of volumetric flow rate, and F1 is equal to F2, which is equal to Fi. So we are trying to say that everything is the same. So in this case, what do we have? We have A dH1 by dt is equal to, I'm going to write the equation directly, which is Fi over A minus alpha 1 square root of H1 divided by area, right? So that is the first equation. And my second equation is dH2 by dt is equal to Fi, F1 in this case, over A1, and in this case F1 is alpha 1 square root of H1, minus F2, which is alpha 2 square root of H2, over A2. Here's A2, right? This one, so the A1 was here and it came up here. The A2 is here and it came up divided by here. Okay, so these are my two systems here. So how I'm going to start with this? I'm going to start building my matrix and look at what I'm going to do here. So x dot, what is x dot in my case here? In my case here, x dot is h1 dot and h2 dot. Okay, so and then we have the matrix A. You remember what we have done? It was df by dh1, and we have df by dfi, but df by dfi, okay, so df by dfi is an input, so we're going to keep this as part of the input. And what I'm trying to build here, I'm trying to build my ax is equal to, my x dot is equal to a x, okay, plus b u, and u is what? U is the input, okay, u is the input. So what I have here, I have x dot, which is h1 dot and h2 dot, okay, h1 dot and h2 dot, and I want to find the matrix A. In this case, I'm going to consider all the partial differential equations. Even though that there's no h2 in my first one, it's like doing the linearization. If I was doing linearization deviation format, here I will consider that I will also take the differential equation with the second height. So the matrix takes into consideration everything, right? Everything. So what I'm going to do, I'm going to take df1 by dh1, and I'm also going to take df1 by dh2, even though that I know that this is equal to 0. So let's continue. Plus b, df by d, so df1 by df1, before I go to this part, I forgot to say something. So now the equation is like h1 dot is equal to df1 by dh1 into h1 prime. Right? You remember that? So this is exactly the equation. H dot is equal to df1 by dh1 into h1 prime. And of course, everything is here at steady state. So how I can fill this? So everything is here at steady state, okay? So here's df1 by dh1 at steady state into h1 prime plus df by dfi, okay? df1 by dfi into what? Into fi prime. This is exactly our solution that we are used to. Okay, we are used to this format. Exactly. Again, h1 dot is equal to df1 by dh1 h1 prime plus df1 by dfi into fi prime. That is the linearization and deviation format that we are used to. However, we added df1 by dh2 into h2 prime. That is equal to 0. But we need to add it because we are building the whole space, the whole possibilities of all partial differential equations. For h2 prime, we are going to do exactly the same. So it's going to be df1 by, it's the second function, df2. If you remember that we said that this is a function of h1 and fi. So we are saying now this is a function of h1, h2, and fi. Okay, so we are taking the possibilities of all state variables and all inputs. Okay, and I think so this is important to say. In this case, we are considering what? We are considering not what is in the equation from state variables. We are considering all state variables and all inputs okay? And this is why I'm including h2 here, okay? And in the A matrix, in which you multiply by h1 prime, you're going to include the state variables, which is h1 and h2. And for B matrix, you're going to include only the inputs, okay, which is df by dfi. So I'm separating at this side the state variables, and on the right hand side, the right side here, I'm stating the inputs. Okay, so let's continue with the second part. So h2 prime is equal to df2 by df2 by dh1, okay, and then df2 by dh2, and that is like that, df2 by dh1 into h1 prime plus df2, the second function, by dh2 into h2 prime. So still by h2 into h2 prime, by h1 into h1 prime, okay, plus df2 by dfi into fi prime. And in this case, I only have fi prime, right? So my matrix is only fi prime, so I have nothing else. So it's only fi prime. So in this case, you can see that it's only one. If there are two inputs, definitely I will have a square matrix here, because I'm going to say df1 by the first input and then df1 by the second input, okay? But in this case, this is what I have. And this is 2 by 1 matrix, and this is 1 by 1 matrix, so the answer is fine. Okay, if you can see here, just look at the matrices. So this is 2 by 1, and the second one is 2 by 2 into 2 by 1. So the answer is 2 by 1, right? 2 by 1. And here it is 2 by 1 into 1 by 1. The answer is also 2 by 1. So you can see that everything is fair and good here. And actually we are already ready here. We just need to substitute the values of df1 and dh1 and df1 and by dh2. So you need to do this, which is not a great deal now for me to do that. But if you like to do it, we are going to do it. We have no problem at all. So df1 by dh1, if you go up there, So if you go up there, df1 by dh1, in this case, it will be 1 over 2 square root of h1 as steady state. Yep, 1 over 2 h1 at steady state under the square root, right? And I will not forget that I have also a1 and alpha 1, right? So I have A1 and alpha 1. So minus alpha 1 divided by A1. And in this case, just to write my A1 correctly, I'm going to say 2A1 here, and this is alpha 1. So this is what I have, df1 by dh1. Okay, again, what is the derivative of that? It's 1 over 2 square root of the height, and we have multiplied by minus alpha 1 over A1. Okay, so what is df1 by dh2? There's no h2, so it's 0. So the second term here is 0. What about df2? This is my second function, right? This is my second function. So df2 by dh1. df2 by dh1 is exactly the same, except that I having like alpha 1 over 2a2 in this case, right? It's 2a2, sorry for that, 2a2 into square root of the height at steady state. And what is df2? df2 by dh2, the second function, I'm taking the partial derivative with h2, which is minus alpha 2 over a2, okay, over 2a2 into 2 of the second height, of a square root of h2 at steady state. So that is my first matrix. So that is A. I already found A. What is going to be B? Sorry, I forgot to add this. This is multiplied by h prime. And then I'm going to add my df by dfi. If you go to the first equation, df1 by dfi is 1 over a1. df2 by fi, there's no fi, so it's 0. Okay, so here it will be 1 over a1, and here it will be 0, and that is multiplied by fi. Okay, that's multiplied by fi. Okay, great. So that is the first part. Now, what about cx plus du? That is a simple part here. I mean, if you consider the simple, this is like even a piece even simpler. Okay, because C is just the identity matrix. And since I have a 2 by 2 here matrix, so I'm going to say C is equal to 1, 1. That's all. What is D? D is the same dimension of that, which are zeros, which is 1 by 2. 2 by 1, which is 0 and 0, and that's all. That's all. And so these are what I got as C. Okay, what I got as C and D. There's one thing that I would try to mention here, is that we said that C, it is used for selecting the type of solution, right? Selecting which solution is required. Which solution is required. And in that case, what I'm trying to say here, which solution is required, is that if I represent my C as what? If I represent C is equal to 1 and 0 only. If I represent C is equal to 1, 0, and I know that this is multiplied, if this is multiplied by h1 prime, like we have cx, right? It's multiplied by h1 prime and h2 prime, right? So what I'm saying here, that I just want the solution of h1 prime. Why is that? Because I have 1 multiplied by h1 prime, so I will have the solution of h1 prime, plus c plus 0 into h2 prime, so I will have no solution for h2 prime. Of course, if I had 0 and 1, I will have the solution of h1 prime and h2 prime, because 0 multiplied by h1 prime, and I will have the solution of h2 prime. Now, if I remove the top and I keep it as 0 and 1, I will have 0 multiplied by h1 prime, right? 0 multiplied by h1 prime, and 1 multiplied by h2 prime. So the solution is only h2 prime. So in this case, if now I decide that I want to keep it like that, only h2 prime will be shown as a solution. Only h2 prime will be shown as a solution. So that is the part of it. So this is how C. So this is how we are dealing with C. It's very easy. It is simple. It's straightforward. I know that you are saying that it's like we didn't learn something new. I know that state space model is easy, and the beauty of the state space model, you just imagine if you have now, if you have like a distillation column, for example, right? If you have a distillation column, and in this distillation column, imagine that at every plate, how does the temperature does change with time. Okay, imagine how many transfer functions you could have here, and how many concentrations you could have here, and how many differential equations. You're having differential equation at every row, right? Yes, it's like you're having a differential equation, or xa by dt, for every row. And imagine how many differential equations you would have. And to make that even simpler for you, it's like I could have here for 60 plates, I will have like 60 outputs, okay, or 60 state variables, and I have like one input, or I could have another reboiler, a reboiler as well, and a condenser here as going back. So what I'm trying to say here, that if I have 10 inputs and 60 outputs, how many transfer functions I will have? I will have 600 transfer functions, okay? Who can deal with 600 transfer functions? It is just crazy. However, all that could appear in what? In just one matrix. It will all appear in this big matrix. Even if it was 100 by 100, it is still one matrix, and it can be solved directly. So this is the beauty of the state space models, that you can have everything in one. However, in the state space model, it's difficult to understand when you look at numbers. If you look at these numbers, it's difficult to understand what's going on. However, in transfer functions, it was good to see the effect of k and tau. You can see the gain, the sensitivity of the process, and the transfer function. So there is also a benefit in the transfer function, that you can understand the process, and this is very important, by the way, because if anything goes wrong, you always go back to understanding the process. However, for solution and quick, and for big systems, the state space model will help a lot for the controllability of the whole plant. Okay, so you want to talk about the whole plant, state space model will do a really good job. Okay. What else do we have? So are we going to have a third example? Why not? Why not? We are going to have a third example. And all our examples are like some problems I'm taking. So here we are going to have a third example. And in this third example, I'm thinking of taking like an example that has the mixer, the blending process. If you remember the mixer, or the blending process. And here, when we have a mixer, I don't know if you can recall what was the equations that we have obtained. You could go back and find out what were the equations that we have obtained, but we had equations that looked like that. dv by dt is equal to 1 over rho into w1 plus w2 minus w3, okay? And we had another equation which was how to find x, and dx by dt was equal to w1 over rho v, okay? And if you remember that w1 over rho v, I don't know if you remember this or not. I'm just trying to recall if you remember that. It was w1 over rho v, and even myself, I'm trying to recall from what I have in my head, if that was a correct term or not. Okay, that is multiplied by x2 minus x. Okay, so this is kind of an example. I know the transfer functions that could come to your head, like especially if I want to find here dh by dt, which makes more sense. Okay, which makes more sense in my mind here. So I will have rho, I will have the area going out, I'll keep the area here. So this is a kind of what I have. I have how the height changes with time, and how I have the composition changing with time because of the mixing process, that I have here. So in this system, how can I represent my system here? If you look at it, I'll tell you what are the relationship in transfer functions, okay? So that I can find how height changes with W1, which are the input flow rates, right? The input flow rates. So for the W1, I also can find how the height changes if W2 changes. I also can find how height changes if W3 is changing. I also can find how the composition is changing if W1 is changing. I also can find X if W2 is changing. Imagine how many transfer functions that I have here. And that's not all, right? I still can go on and put all my transfer functions that I could have here. And I just wanted to give this example just to show you like the amount of transfer functions that you can have. Okay, so in this case, what do I have? I have two state variables, and how many inputs I have? 1, 2, 3. Okay, 1, 2, 3, 4, 5. Oh, okay, I don't have x3, 4, 5. So all what I have here is how many again, how many inputs I said that I have W1, W2, W3, X1 and X2. So how many I do have here? I have 5 inputs. How many state variables? I have 2. So I should have 10 transfer function. It's like the number of state variables multiplied by the number of inputs. Okay, or did I say that? So it's number of state variables multiplied by number of inputs. So I have here 2 multiplied by 5 is equal to 10. In this case, I have 10. What about, did I say W3 is yeah, W3 also could be some kind of an input here. Okay, so what did I find? I found 1, 2, 3, 4, 5, 6, 7, 8. So what did I forget here? What did I forget? So I have H that could be changing also with, you see, I forgot that H could be changing because of X1, even though that I know that this could be of no sense, but these are all the possibilities that I have. Now if you count them, like if you count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I have 10 transfer functions. Well, was my aim to find out the transfer functions? No, that was not my aim. My aim is to do the state space modeling system, right? That is my goal. And if this is my goal, so I need to put things as to my goal. So let's do the state space model. So going back to the equation that I have here, I just want to remind you that when we solved the mixture last time, we said that the volume is constant. So we made this whole term equal to 0. But by the way, you can keep it as a variable if we consider that it's a variable. And if you consider it as a variable, things of course are going to be changing here. And if you recall, it's just that I felt that you're not really solid of what we have solved here. So let me solve it again for the mixture. So if I say that dm by dt is equal to mn minus m out, I'm just developing the model equations again for you to feel comfortable about. However, I'll start to skip some parts here. So dm by dt is equal to the w1 plus w2 minus w3, right? So that was my first part. Of course, if I want to find how dh by dt is changing, I can do that. dh by dt is equal to 1 over rho a into w1 plus w2 minus w3. Okay, so I think that you are happier now that you know that, okay, this is the equation that we know. Great. And what else do we have? Then we went to dma by dt. Okay, we did the component mass balance. So let me say here, this was the overall mass balance. Okay, if I can do the component mass balance just by side here. So the component mass balance that we had done was like dma by dt rather than just m for the overall will be how much is in and how much is out. Okay, how much in and how much is out, which if I'm going to write this in terms of w, so that is wa1 plus wa2 minus wa3. And in this case, ma is the composition to mass, so that will be composition into mass. I think you remember that. by dt. WA1, I can represent this as x1a into W1, and WA2, I can represent this as x2a into W2, and W3 as x3a into W3. Okay, and then we said that this term here is a multiplication of two differential equations. So xa3 into dm by dt, and dm by dt, we already have dm by dt here, right? So we can use the dm by dt here to substitute here, right? To substitute here when we have the multiplication. And here I'm going to skip up terms, if you excuse me, so that I'm just going to write the direct final equations that we had obtained. So in this case, I want to know how much x3 is leaving the system, how the composition is changing, which is equal to W1 over m, and in this case m is rho a into v. I don't know if you want to put this as m or what, but if you want to put it as m, let's put it as m. So it's okay. I'm going to put it like m, which is rho into volume, which is rho ah. I'm going to do that, which is multiplied by x1a minus x3a and plus W2 over rho ah into x2a minus x3a. Okay, great. So this is what we have as a system, as you can see in front of us. And if I'm going to do, if I have like a mixture thing, I'm trying to mix water and whatever, and this is what I have as a system as x3a. Great. So now with the equations that I have like, this is my equation here, and I have another equation which is the dh by dt. Okay, so it's like I have this equation and that equation there. So very nicely I tried to keep them beside each other. That was my goal, so that I can do my differential thing here. Okay, so with the space that I have, without these things that are appearing in front of my eyes, okay, it's always nice to be able to hide these things. It's not easy. We'll do this as sometime later. Okay, so what do we have here? If you can recall, I'm trying to build up my x dot, which is equal to ax plus bu. And in this case, what is x dot? X dot is my system here, right? X dot is h dot and x3a dot. And what is the matrix A? Matrix A is the first function, so I have the first function here. Okay, this is a function of all the state variables, which is h and x3a, and all the input variables. What are the input variables? I have w1, w2, and w3. Okay, maybe there is one input variable that is appearing here, so I may forget it. Okay, so just to make sure, the function 2, which is a function of all state variables, which is in this case again h and x3a, and all the inputs, which is w1, w2, w3. I forgot some inputs: x1a, x2a, and x3a. Okay, in this case, what I'm going to say, well, I need to add those inputs. Okay, so I will have here x1a, x2a, x2a, that's all. Why is x3a? x3a is one of my state variables, right? Okay, so how many inputs I am having? I have 5 inputs. That's fine. We already said that we have 5 inputs, so come on. I already forgot this. So this is what we have, and what we are trying to build here, as I said, we are trying to build our x is equal to ax plus bu. So this is what we're trying to build here. So what do we have? Let's start our system. I may not attempt to find out the whole terms, but I will do the attempt of doing the partial differential thing. So I have df1. So I'm here. Just remember, this is a multiplied by what? Multiplied by the h dot. The x. X is h and x3a. And this x and h3a are related to what? Are related to the dot. So x, x dot, h dot, x3a dot, x dot. So I'm just repeating this just to see it. And looking at our system here, so I have df1 by df1 by dh at steady state, and then I have df1 by dx3a at steady state, and then I have df2 by dh at steady state, and df2 by dx3a at steady state. Okay, so that is I think so I did this in a bigger font, so dx3a at steady state. Okay, I know this is small, but it's good enough for you to look at it. You can zoom in. So plus b, and here b, if you can recall, we have 5 inputs, so that is going to be a big matrix for us. So we have 5 inputs. Okay, and what are the 5 inputs? If you can recall them, we put them in order, and the order is important. So w1, w2, w3, x1a, and x2a. Okay, so this is my matrix here. So what I have is I have df1 by dw1, of course, at steady state. And here I'm not going to put at steady state. It is at steady state, by the way, but just to save my space here. Okay, and not to confuse things getting inside each other. So I have df1, sorry, so here's all df1 by dw2, df1 by dxa1, I forgot 3, okay, so that's dw3, and df1 by dxa1, and df1 by dxa2, and then you have the partial differential of the second function, the differential equation, by d1, and then the second partial differential equation by, did I skip things? Here's 1, okay, and then df2 by dw2, df2 by dw3, df2 by dxa1, and df2 by dxa2. Okay, so this is my big matrix that I have, right? That is my big matrix that I have for my system here. And now considering the solution, y is equal to cx, y is equal to cx plus du, and as I said, c is the identity matrix. So my a was, if I look at my a here was 2 by 2, so my c is going to be just a 2 by 2 matrix. And in this case, my d is a big one. My d here, my d was really a big one, right? So my d should be like my b. My d should be like my b, okay? D, b sounds similar sometimes. So d here is going to be all zeros, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay? This is my d. And that is my solution. That's my solution. Of course, the solution is when you substitute all the values here. And depends on the question if I ask you to calculate these values or just to put the main matrices without finding the answers of the partial differential equations. So that is state space modeling. That is state space modeling of what you can see here. Okay. Now, there's something in state space modeling which is little different, and usually you find this when you go to people who teach physics or electrical engineering. They do explain state space modeling in the way that I will try to represent here, and I'm trying to represent it here. Please look at it, and we are going to do this step by step just to keep it also simple for you. Okay, so if we say that we have now already a differential equation in front of our eyes. Okay, so one more example, and we are done with state space modeling. So for example, I have 5dx to the power 4 by oh my god, how should I write this? This is like the fourth derivative. And instead of saying the fourth derivative, what I'm going to do here, I'll keep my life easier. So I'm going to use y, okay? I'm going to use y. So y, the fourth derivative, Can you see the 4? Okay, plus 3 in third derivative plus 2 into the second derivative plus y in the first derivative plus y, and if you want to put minus, please put minus. I mean, it's equal to 3, right? So I'm just trying to build my system here, and so I'm just giving an example, a very arbitrary example, so that we can start solving our solution. Is equal to 3u. So now if I consider this problem that I have here, this is what I will try to do here. Okay, so bear with me. So if I call this like for example, I have here, this is equal to x1. Okay, this is like it is equal to x1, and I'll call this x2. Actually, I also can start from the y where I say that it is x1. So I'll say like this is x1, this is x2, this is x3, this is x4, and that we are going to represent as x5, and we see how it will look like in a moment. Okay, I know this is tricky, but we are trying to take the higher differential equation of a fourth or a third order to a single first order differential equation. That's the whole idea. Okay, and so what I'm trying to do here, I'm trying to transform the higher order of differential equations to what? To a first order differential equation, Okay, so this is what I'm trying to do here, and you're going to see how this is done. Okay, so what do we have here? So now, after I said that this is like x1, x2, x3, x4, and x5, what do I have? I will keep x1 as normal. Actually, x2 is equal to x1 dot, right? Because x2 is the differential of that one, y dot. And x3 is equal to x2 dot, because this y double dot is the differential of this y dot. You see how tricky was that? X4 is equal to x3 dot. And this one is already x4 dot, right? Which is x5. Okay, why are we doing this? Now we can see this single differential equations in all our terms. So if I write all my equations, what are my equations here? I have many equations. Okay, so I have one equation, two equations, three equations, and I have my main equation that still remains. Okay, and I want to appear all what I have written as an equation in the format of x dot is equal to ax plus bu. And in this case, if I want to represent that as x dot is equal to ax plus bu, I'm going to start with the main equation here, the big one, and I'm going to rearrange that. So I have x4 dot is equal to, I'm going to take everything to the right hand side to be ax plus bu, and in this case I'm going to write them one by one. So this will be like minus 3x4 minus 2x3 minus x2 minus x1 plus 3u. Okay, so that was my first part of the equation. What about the second ones that I do have here? I have the second one here is x3 dot is equal to x4. So x3 dot is equal to x4. What's the next? Is x3 is equal to x2 dot is equal to x3. So x2 dot is equal to x3. And I did on purpose that I kept a space here just to say that how it's x3 and all the rest are zeros. And then I'm going to have my x1 dot is equal to x2. My x1 dot is equal to x2. Did you see this? That everything is really beautifully written. And what else? These are my equations. So I have like 1, 2, 3, 4, 5 equations here. And then looking at these 5 equations that I have, very simply I can build my matrix. And my matrix will be like, I need to rearrange them, right? This looks like, oh sorry, I have 4 equations here. I have 4 equations. It's a 4th order, so that's why I have 4 equations. So I have x1 dot, x2 dot, x3 dot, x4 dot. I think I presented everything as in the opposite direction. Never mind. So that is x dot is equal to ax, and a in this sense, which is, if you can recall, df1 by dx4. df, because I did everything by opposites, okay? So df1 by dx3, df1 by dx2, df1 by dx1, and then you go to the second equation. Okay, so that these are my equations. Like, this is the first equation, second, third, fourth. So you will have a matrix like df2 by dx4 and continue, df3 by dx4 and continue, df4 by dx4 and continue. Okay, and you're going to do the same here for the df1. Let me see here. Okay, there's something that I don't want you to get confused with, because I'm calling this function 1, function 2. Okay, I'm calling this function 1, 2, 3 and 4, right? And I'm presenting here as x4, x3, x2, x1. Okay, so I'm representing here as x4, x3, x2, x1. So the first one is f1, then that is fine. Because I did not put things in order, it became a bit confusing. If you feel confused, if you just want to change this f4, because it doesn't matter how that will appear as long as you are writing the equation correctly here. So you see, x4 dot is equal to the function of f of this x4 by x4, because you're multiplying by x4 here. Okay, but if you feel confusing, if you want to keep everything as you're used to, and I have made everything the other way around, you can just put things like, just to be x4 with function 4, right, and f3 with function 3. This is just kind of something that if you like to do, as long as you get everything correctly. And here x4, x3, x2, 1, because I'm doing df4 by dx4 into x4 prime. It should look like that, right? By dx4 into x4 prime, by dx3 into x3 prime, by dx2 into x2 prime, dx1 to x1 prime, and then again dx4 to x4 prime, dx3 to x3 prime, and so on. So this is what I have as the equation here. And as you can see, if you want to substitute, before I substitute, let me just put the final part here. So it's like I said df4 by, now how many inputs I have? Just one input, so it's du, and df3 by du, and df2 by du, and df1 by du. Okay, and that is multiplied by u. And now if I want to substitute, things are going to be easy, because for df4 by dx4 for the first function, I have -3, so I'm just going to put them, right? df4 by dx4 is -3, df4 by dx3 is -2, df4 by dx2 is -1, and so on. Okay, so I'm going to put the numbers -3, -2, -1, -1, -2, -1, -1, and that is multiplied by this term here, plus I think it is 3 here, right? 3 in the first one, and multiplied by u. And if you go to the second function, actually the second function we have only x4, all the rest are zeros. Okay, x4, all the rest, x4, which is 1, and then all the rest are zeros, and then I will have 0, or 1, 0, 0, and then I will have 0, 0, 1, because x2 here is 1 out, we don't have the rest. Okay, so I just solved that for you. Okay, and here the u, you don't have u in the other created the equations that we had done. So that is A and that is B. So that is the matrix A, that is the matrix B, and we can find the matrix C. And finding the matrix C is the same dimension. Of course, the same dimension considering all solutions. So I have here a 4 by 4 matrix, so it's going to be something like that. Okay, so that is a 4 by 4, and for D is the same like B, so it's 4 by 1, so it's going to be 4 by 1. Great, so that is one kind of a problem that was for a state space modeling in which we have a higher order system. Usually we deal with the first type of industries, but I also wanted to mention the other types that are popular in other fields. How do they use state space modeling? Now I want to show you state space modeling if I have a transfer function and how to deal with the state space based on what I have done just now. Okay, so for example, I have this problem here. Okay, so this is like example 5. So I have this standard form of a second order. Do you remember this? I think all of us remember this. Okay, so I have a standard form. I'm just going to keep K as 1 for simplicity. So this is a second order system, right? It's a second order system. If you want to put K, let us put K. Just to say that this is the standard form for any case. And now if you cross multiply, okay, we are cross multiplying here. We are going to get a system which looks like that: tau square s square y of s plus 2 xi tau s y of s plus y of s is equal to k x of s. And this looks like very similar to the example that we have taken. Why? Because actually if you take the Laplace inverse, if we take the Laplace inverse here, what you're going to get, you're going to have s square y square. If you recall, s square y of s is the second derivative, sy of s is the first derivative, and very beautifully you can see that this will appear like tau square y of t of second derivative, okay, plus 2 xi tau for y of t of the first derivative plus y of t, okay, is equal to u of t, right? U of t, in this case k u of t, right? And this is exactly what I have, exactly as a system that that's represented as a second order, and as in the form that I just had solved from a moment. Okay, so what I was talking about, I will consider this as x1, and then I'm going to consider this as x2, right? And I'm going to consider this as x3. And here we know that x1, the x2 is going to be the derivative of x1. And here x3, I'm just going to call it x2 dot, okay, rather than x3, because we will have no first differential equation then. So if I'm going to rewrite this again, this will be like tau square x2 dot plus 2 xi tau x1 dot plus x1 is equal to k u of t. And here I have two state variables. If you can see, like, what are the equations that I have? I have this equation here, okay, so I have this equation here, and I have another equation here. So I have two equations in this case. If I want to rewrite this equation, and I want to write it in a form that looks like that: x dot is equal to ax plus bu. Okay, and on rewriting it as this form, I'm going to have x1 dot is equal to x2, and this is obtained from here. If you can see, x1 dot is equal to x2, and I have x2 dot, and I'm going to take everything to the right hand side, and I keep just x2 dot on the left hand side by itself. So this will be minus 2 minus 2 xi tau x2 divided by tau square minus 1 over tau square x1 plus I think so I just missed the k here because I already solved the example without the k, so just let me make sure. So this is k here. That's only the k that I forgot. Okay, great. So what do we have here? We'll have like tau cancelling out with 1 tau here. So that's all. So my x2 dot, my equation here, if just I want to put it in a better format, I'm going to remove this tau and tau. So this will be x2 over tau. Okay. So that is my equation here. I have two equations, and if I want to represent that, that is x1 dot x2 dot is equal to the first function by dx, the first function by df1. So what is f1 and f2? Just to make ourselves clear, this is f1 and this is f2. So the first function by dx1 and dx2, right? Why? Because I have here x1 and x2. So my df1 by dx1 for the first function is 0 and df by dx2 is 1. Here you see by df by dx1 there's no x1, df by dx2 I have 1. Okay, so that is the problem here. And continuing, I'm going to have the second derivative df2 by dx1, and I have x1 here, and then df by df2 I have x2 here. So this will be minus 1 over tau square, and then I'm going to have minus 2 xi over tau, minus 2 xi over tau. Great. So that's multiplied by x1 over i2. Then df1 by dx1 by du1, I have no u in the first equation, and for my second equation for x2 dot, I have u here. So if I take the derivative, partial derivative with u, it would go to k over tau square, and this is multiplied by u. So that is my solution. And actually this is not the solution, this is just the matrix. I can enter this matrix, and I can enter this matrix, and y is equal to cx plus du, which is the solution, where c is going to be equal to 1 1 0 0. If I only want to find x1 dot, I'm going to consider only this part here, 1 0. If I want to find only x2 dot, I'm going to enter only 0 1. If I want to find both of them, I'm going to enter this whole term, as we had said earlier. And here d would be the same dimension of b, which is 0 and 0. Okay, so these are the main things that you really need to do here. So what we have done, we have taken a transfer function to a state space representation. Okay, it's transfer function to a state space representation, and this is all what you need to do. There is something that if you want to turn state space representation to transfer function, okay. So what we have done, we have taken. Let me write that. So state space representation to transfer function. And what we have done, actually, we have taken our transfer function. This is what we have done here in this example. In this example, we have taken our transfer function, into a state space format. Actually, we took it to the time domain, and then we have taken that into a state space format. Okay, and now what we are talking about is that you could do the other way around as well, but doing the other way around, it will need some kind of knowledge about matrices, and I'm not sure that we are going to be taking this example in the exam. I don't think so I'm going to bring in the exam, but it's a good idea if you just have an idea about how it is done. So it's like if I have x dot is equal to ax plus bu, and y is equal to cx plus du. The question is that if you apply Laplace transform here, so you see, if you apply Laplace transform here, what is going to be happening? We know that x dot, the Laplace of a differential equation is s, x of s, right? And this is going to be a x of s plus b u of s. And for the second equation, this is going to, let me continue the x of s, which is of the first part. Okay, so the first part, we're going to continue x of s. Well, I think so. You already you can see that I can take a common factor of x of s, and x of s into s, right? But we don't usually put just s, like we put an identity matrix of into s minus a, and this is the way how you present it. You present 1 in the matrices. How do you present 1 in matrices? Usually represented as identity matrix. Okay, so that is the idea that you need to know here. Okay, so continuing on, this is equal to b u s, and if I want to find x, of course, if I want to take this to the other side, taking this to the other side is not divide, is the inverse. Okay, and this is the second thing that you need to remember about matrices. So this is like inverse into bu of s. So I'm sure that this is not difficult. This is just the idea that you need to remember things. Now, what was my solution? My solution, if you can recall, it was y of x is equal to c x plus du, and I'm here representing it as the Laplace, taking the Laplace of it. What I'm going to do here, very simple. I'm going to substitute x into my y of s so that I can find the solution of y. And in this case, if I do this, I'm going to get a bigger term, and this bigger term is going to be c into is minus a. If you can recall this was the inverse into b u of s, right, plus d u of s. Okay, so this is like I substituted, and now I want to represent that into as my normal representation of a transfer function of an output over an input after taking a common factor of u and taking it to the left hand side. So I'm going to be left with the right hand side, which is c into is minus a inverse, okay, into b plus d. Okay, and here is minus a is like you just need to remember that if you have like if you have a matrix which is 2 by 2 matrix, you need to know how to find this is minus a, right? So if you have a 2 by 2 matrix, for example, which is like a b c d, and the way of how to take the inverse of a matrix. Okay, so here I'm saying that how to take the inverse of a 2 by 2 matrix. And the way of how to do the inverse of a 2 by 2 matrix is to do what? Is to do this 1 over determinant of this e, if I call this e, okay, if I call this e, into dA, you just replace them and you just change the sign. It's just something that you could memorize here. And the last thing that I'm going to say, that now we can see that this is in the denominator, and and usually you say that in the denominator, if we have like negative poles, it's going to be constant. And in this case, if you put this determinant is minus a is equal to 0, which are the poles in this case. And what I want to mention here is that the eigenvalues, we are not going to study the eigenvalues here, but I'm talking about the eigenvalues of matrix A. Okay, the eigenvalues of matrix A. Okay, what was matrix A? It is the df by d functions, right? So the matrix A, the eigenvalues are the poles of the system, it will so if I want to know in transfer functions if the system is stable, I can look at the poles, and if I want to know that my matrix A is stable, I can look at the eigenvalues. Okay, and we can get directly eigenvalues by putting it in MATLAB without any calculations. It's just like EIG, I think so, and you find the values there. Great. So this is all about the state space modeling. We have taken many examples. The main examples are the one which is reflected on industry. You need to know how to shift state space to transfer function, at least as a knowledge. But definitely you need to know how to shift this transfer function into a state space format. Okay. So you need to know how to shift from one place to another. But other than that, you need to know how to find the A, B, C, and D matrices. Okay, how to find A, B, and C, D matrices for the systems that we have represented, either for the mixer or for the tanks that we have represented here, right? For the tanks that we had represented. All till then, all the best, and I think so that we had done a very good job today. And this is our happy face today. Oh my God, a big hair, big eyes, and very smiley face. And I wish I can draw better than that. I mean, this is my best, but I like always to show that we are happy. We need to reward ourselves to what we have achieved. Thank you very much. All the best. Ma salama.